Let's find the location of the other Lagrangian points. So these are the derivatives of the Jacobi constant, the two equations that have to go to zero, so that the velocity is equal to zero and we have equilibrium in the rotating frame. We found the two solutions, which are the triangular point L4 and L5. The other three solutions we find by realizing that the second equation goes to zero when y is equal to zero. Therefore, it's only the first solution. Therefore, it's only the first equation that we need to solve. This first equation then will give us the collinear Lagrangian points. They're going to lie on a line along the x-axis and the line joining the two masses. So let's find then where these points L1, L2, and L3 are. First, why there should be 3 points? Well, let's put the two masses on a line. So this is the mass 1 and this is the mass 2. There are 3 Lagrangian points because if they lie on a line, there are 3 positions for it to be. It can be somewhere to the left of the primary, it can be somewhere in the middle between the masses, or it can be to the right of the secondary. So this would be then the Lagrangian points L3, it's to the left of the primary, L1, it's between the masses, and L2 is to the right. So how do we find their locations? Well, let's look at the geometry of the problem. You have that R1 is going from the primary to the Lagrangian point. And of course, the central mass is along the line joining the primary and the secondary. The distance from the primary to the central mass is mu2. The distance from the central mass to the secondary is mu1. So x of the Lagrangian point is here from the central mass to the L1. And then we have the distances from the primary to the Lagrangian point, that's R1. And the distance from the secondary to the Lagrangian point, L1, that would be R2. So just based on this geometry, then we can write R1 is equal to x plus mu2, and R2 is equal to mu1 minus x. So from these equations, you find that the derivative of R1 with respect to x is equal to 1, and the derivative of R2 with respect to x is equal to minus 1. Also, if you sum them both, then you cut the x's, and then R1 plus R2 is equal to mu1 plus mu2, which is equal to 1. So let's use then these constraints on the equation for the equilibrium point. If x plus mu2 is equal to R1, then this first term is equal to 1. And if x minus mu1 is equal to minus R2, then this term then is equal to minus 1. This equation then becomes mu1 times minus 1 over R1 squared plus R1 minus mu2 minus 1 over R2 squared plus R2 is equal to 0. Now let's use the other constraint that we have, that R1 plus R2 is equal to 1. So substitute R1 by 1 minus R2 and back in the first equation. Now let's put the terms on the left-hand side under the same denominator. That is, this becomes 1 minus R2 cubed, and the same thing with the terms on the right-hand side. Now let's multiply both sides by minus 1. And expand now this cube, this 1 minus R2 cube, remembering that 1 minus x cubed it's 1 minus 3x plus 3x squared minus x cubed. So I have that the 1 will cut with this one, and this equation is mu1 3r2 minus 3r2 squared plus r2 cubed over 1 minus r2 squared is equal to mu2 1 minus r2 cubed over r2 squared. Now multiply both sides by the denominators to get rid of them, and extract here 3r2 from all terms. And since R2 is a location of the equilibrium point closer to the planet, which is a lower mass, we make the approximation that R2 is much, much less than 1. And let's see then a posteriori if this holds. But if you do make this approximation that R2 is much, much less than 1, then you can get rid of this linear term, and this quadratic term, and this term, and also this term here. So you end up with something very simple for R2. You find that R2 for this L1 equilibrium point is equal to the cubic root of mu2 over 3 mu1. You may recognize this as the Hill radius of the planet. which is the point where the gravity of the planet, the gravity of the star, and the centrifugal force cancel out, also known as the sphere of gravitational influence of the planet. So we found the location of L1. It's 1 Hill radius away from the planet towards the direction of the star. This distance here is equal to the Hill radius, which is a cubic root of 1/3 of the mass ratio of the planet to the star. Okay, now let's do the same analysis for L2. X is the position between the central mass and L2. R2 is the position from the secondary to the L2 point. And R1 is the distance from the primary to the L2 point. From this, then you have that R1 is equal to x plus mu2, and R2 is equal to x minus mu1. So the derivative of R1 with respect to x is equal to 1, and so is the derivative of R2 with respect to x. And if you subtract one from the other, then you have the R1 minus R2 is equal to 1. So I have here x plus mu2 is going to give you 1, and x minus mu1 is going to give you R2, is going to give you 1 also. It turns out the analysis leads to the same result. The R2 is equal also to mu2 over 3 mu1 and the cubic root. So L2 is symmetrically with respect to the planet to L1. It is another Hill radius away, but in the direction opposite to the star. This distance is also a distance equal to the Hill radius. Now let's see the point L3. L3 is at this distance x, which is negative, with respect to the central mass. We have the distance R1, which is from the star to L3, and the distance R2, which is from the planet to L3. Now, because x is negative, then the distance R1, which is by definition positive, is equal to minus x, which is a positive quantity, minus mu2, and R2, which again by definition is positive, is equal to minus x plus mu1. So dr1 dx is equal to dr2 dx, and they're both equal to minus 1. Now if you subtract R2 from R1, then you have mu1 plus mu2, that's equal to 1. So let's go back to the equation. So x plus mu2 is equal to minus R1, so this term gives you minus 1. And x minus mu1 is also equal to minus R2, so that gives you minus 1. So the equation that you have then is the same that you had before. And now let's use the fact that R2 minus R1 is equal to 1, and then substitute R2 is equal to 1 plus R1. And doing the same thing we did before, let's put everything under the same denominator. Then you have mu1 over mu2 over mu1 is going to be equal to 1 minus R1 cubed, 1 plus R1 squared over R1 cubed, R1 squared plus 3R1 plus 3. Now let's substitute R1, which is the distance from the primary to the equilibrium point. Let's substitute it as 1, the semi-major axis, plus beta, a quantity that we don't know yet. With the substitution, then mu1 over mu2 becomes beta square 1 minus 1 plus beta cube, 1 plus b cube, now 1 plus b cube plus 3, 1 plus beta plus 3. So let's expand this cube here. That will lead to cut the 1 and extract a beta from what is inside this parenthesis, and we have beta cube 3 plus 3 beta plus beta cube over 3 plus beta squared. And in the denominator, 1 plus beta cube, 3 plus 3 of 1 plus beta, plus 1 plus beta squared. So now make the educated guess that beta must be much, much less than 1, and see where that leads us. So if beta is much, much less than 1, then you can cut to this beta squared, you can cut to this also, this one, and this, as well as this one. And what you have then is beta cube here, then 3 over 7. So approximately beta cube. So if you take then the cubic root of this, so beta is approximately the cubic root of mu2 over 1. So even for the case of Jupiter, where the mass ratio is 10 to the minus 3, that would give you about 10 to the minus 1. So indeed, even for the most massive planet, beta is still much, much less than 1. So the assumption that we made about beta is justified. So we find that for the point L3, R1, which was 1 plus beta, if beta is much, much less than 1, R1 is about the same as the semi-major axis of the two-body problem. So indeed, we find that the L3 must lie then on the opposite side of the orbit. This distance between L3 and the star is about the same as the semi-major axis of the primary.